there's some more comfortable seats at the front. It's okay. Just spread out a bit. There's plenty of seats. Spread out. Okay. Okay, we'll get started. There's a few more drifting in, but we'll start. Yeah. So good morning again. Morning, yes. Oh, thank you. I'm David Harvey, as you know, Professor of Electronic Engineering at Liverpool John Moores University in the UK. And as you heard earlier, I've been associated with this college since I first visited 22 years ago on this design centre project. So I know what a good college it is. So all the people from here, well done for getting here. And all the people who come in for the course, it is a good college. And hopefully I can build on that reputation. So this morning's an introductory lecture taking you up to the lunch. So the first bit's a bit general, give you the overall idea where electronics might be going. And part of the lecture I'll be asking you questions, so you can't go asleep. So it's not just me talking, okay? Later on I'm doing a design example, very simple one, on the whiteboard, because some people may not have done any clock design before, so I'm just going to overview what clock design is, for anyone who's not a digital designer. And the same thing tomorrow, looking ahead, I'll be doing an overview on what asynchronous design is, which not many people do, but I'm very keen on. One of your faculty members said, well, when I came in 1996, I gave a talk in computer science department about asynchronous design, saying it's the next best thing. That's 1996. It's still coming. So if you stay around long enough, it will come, and then we'll get more on that later. Also, as part of the course, we're looking at the reliability and validation of circuits, but not just the circuits, how you might build a circuit and put in a component, which is a motor car or a scooter. Lots of scooters around here, and reliability is key. And mobile phones I'm going to start off with, just to see what you think about mobile phones. Anyway, we'll get started on here. So it's really talking about modern digital electronic design and a little bit of background after that. So the first slides are showing you how far we've advanced since 1983. Some of you probably weren't even born then. Possibly, I don't know. So this isn't the very first, but this was one of the first mobile phones that became popular, Motorola. Motorola were a semiconductor chip manufacturer, and made chips and made some very good microprocessors in the early days, but they got involved in mobile phones. We used to call it in the UK, it's like a house brick. Most people didn't own them, they're too expensive. Maybe salesmen or directors of institutes or MDs. Most people didn't afford it. And you see how big it is. And that sort of transistor in that generation was this bipolar junction transistor. And looking at the size of a junction, the size of a transistor, as we'll see this week, is very important. Small isn't necessarily better, okay? People will tell you that. What you want to do with a transistor is use the transistor that will do the job for engineers. So transistors then are about 1 micron, that's measuring across the junction. Sometimes they call it a line width later on when it gets to silicon technology. But yeah, 1 micron is quite small. Can you picture what 1 micron is? 10 to the minus 6 of a meter. Try and imagine how small that is. Difficult to do. And a bit later, Nokia became the kings of a mobile phone for quite some time. And I've still got a Nokia phone from this generation. No smartphone for me. And it still works. Okay, quite robust, but mine's a slightly later model. It's got a colour screen, but at this time you see transistors structured like this. It's a field effect transistor, FET we call it, and the size has gone down by 97 to about a quarter of a micron. So that's 4 times smaller. Doesn't sound a lot, but the technology and the physics to do that is very difficult. Then how do you make it? You know, it's difficult enough to solder one transistor. How do you make something that small? So a lot of investment has to go behind tech, and still is. So the next one. Now this is where I've never had a mobile phone this new. Okay. The Motorola was still in the market here. You've got this Razr. This is a very popular phone, like a flip phone. You've probably seen that. People used to like this a lot, you know, and you see transistors moved on again. 2004, we're now talking about MOSFETs. 2D means 2-dimensional, and the size has gone down to 0.13 of a micron, or we could say 130 nanometers. That's 10 to the minus 9. So go back, so it's 0.25 of a micron in 97, it's 0.13 in 2004. So I'm going to ask you a question now. For most of you will have smartphones because you're high-tech, younger than me. You want to send all these messages. So this type of thing, Motorola now, more or less disappeared from the market, as far as I know. Nokia's disappeared more or less, but trying to come back. iPhones come in, and Samsung, and one or two others. But if you look at the Samsung Galaxy S8, which is a popular one, you've now gone to this 10 nanometer size in 2017. And that's a FinFET. Have you heard of a FinFET? So FinFET is 3D transistor. So someone's had the idea, a researcher, it's been developed, and Intel have taken this on in their chip. So instead of just having planar transistors, now the gate's going up. So you're not just going in the X and Y direction, you're going in the Z direction. So you can get even more transistors on the chip. So 10 nanometers. And the next step is supposed to be going up into 7 nanometers. Tends to go in 0.7, then probably 5 nanometers, and maybe 3. And I'm not sure I can go beyond that. So it's difficult. So you've all got smartphones. How reliable is your smartphone? How long will it last? How long will it last before it breaks? Is it very reliable? Yeah, smart, reliable, but not big, don't it? Phones are great unless you drop them. The electronics is pretty stable. But how long do you think? How long do you think a smartphone would last? No idea. Do you know why a smartphone's so reliable? You only keep it 2 years. Then the new one comes out. If you go to mine, I've got this type. I've had mine 20 years. The only thing I changed was one battery that cost me £1 on the internet. And my battery lasts longer than yours. So it's not just about the electronics. Inside this phone, I'll just tell you a short story because we've got enough time. You've got battery technology. Battery technology has moved on these lithium batteries. They can go on fire, which hopefully they don't, but they can give a lot of power. But then because they give a lot of power, more applications inside the phone. So when I was coming here, if I'm going to India, I've been here before, sometimes you might have a power cut. So I might want to buy a torch. Okay? So I went to the airport, I went to the shop before. It's difficult to buy a torch in the UK. And do you know why? What do you have on your phones? If you go to Eden Gardens, everyone's shining the lights on the torch. You go to a concert in the UK, they all shine lights. My phone hasn't got a torch. So I've been overtaken by technology, so now I need to buy a torch. But even torches, I was thinking about it this morning. Torches used to be a battery and a bulb. Even now torches are high-tech. You've got LED torches, very bright, strong batteries. Torch will probably recharge, plug it into the USB. Okay, anyway. It's about phones. So the thing that I concentrate in my research at the moment is I'm looking at the reliability of solder joints. Because the thing that's most likely to break once you've manufactured a phone or any other product is the solder, because that's connecting everything together. Now, we've all done soldering. Have you done soldering in your courses? Now, to be lead solder, now it's on lead-free, which is slightly more brittle, so it's created more problems for the environmental aspect. You don't want to use lead in products. So look at this chip over here. This is a normal PCB, and normally you just solder a chip like this with solder. These are balls of solder, we call it solder balls, onto the chip. That's just the basic chip, and that's used in nearly all the big chips now. Why do you use solder balls is the first point. Well, in the old days you used plated through holes. Have you seen these? And it's nice to make as a hobby. You drill the board with the holes, you make the circuit board, you solder it on the reverse side. Quite difficult to make when it's automated. If you don't spread if the chip comes bowed out, you have to put it through a process to bend it so it's parallel, insert the chip into the board, the automatic soldering wave machine will solder it. Anything goes wrong, the chip gets bent or it gets misplaced, a lot of things can go wrong. But it's easy to test. You can get your probe, put it onto the solder joints, and they're quite big, 0.1 of an inch in those days. So easy to test. These things, impossible really to test, which is why I'm going to teach you new ways of test this week. You can't get a probe in there, as we'll see later on this afternoon. So these spacings might be 0.5 millimeter. You can probably, if you're clever, just put a probe on with a sharp point and see what's going on if you want to do some testing on the board. But most of these solder balls are hidden. You've got a 2D solder package there underneath the package. You can't get any probe there, and you can't see them with the naked eye or the camera. So how would you test it if there's a fault? Very difficult. And that's not just the start. You've got solder balls there, and there could be hundreds, even 1,000 solder balls on a package. One solder ball isn't made correctly, it doesn't work. So manufacturing is really difficult. And in this one, you've got what we call different things, multi-chip module, stuff like this, more than one chip in a module. So here you've got multiple die on the top, with only 2 shown, but you could have more than 2. Then they're all connected through. These are the latest things for connection. We used to use bond wires, now we use what we call TSVs, which are through silicon wires. So silicon to silicon connections, and you get problems with these as well. And then finally, this is sometimes called an interposer board, with wires on, and sometimes we call this interposer, sometimes for these as well. The names don't really matter. There's different names coming in the market. The trick is there's a lot of layers there, a lot of connections that need to be made, and it's getting smaller. The solder joints are getting smaller. As things get smaller, they're not as strong per joint because it's smaller. So that's another possible problem. And a lot of people don't foresee the problems. I mean, for phones, you can't make a phone that's not reliable. If the latest version of the Apple came out had a major fault, very quickly would find out that you can't sell it. So that's the brief introduction. Now I'm going to talk a little bit about, I'm a digital electronic engineer. It doesn't mean I don't like analog. Everything's digital now, but we still need analog at the front end and the back end. You've got a mobile phone, you've got a microphone. Immediately a microphone will be digitized with an A to D converter, go into digital domain, it's transmitted digitally, goes through around. The only time it really goes analog when you've got the speaker or whatever. So digital is for transmission, digital is for processing. And why is it good? Well, you can make it very small and very efficient. Only switches between 0 and 1. Analog, a lot of things can go wrong. You can pick noise up very easily. Digital, as long as you're not within the noise margin, you're going from 0 to 1, it should work if you do the design correctly. But it's not so easy, as we'll find out. So because it's small and efficient, by efficiency I mean it doesn't use much. So mobile devices, I know there's a problem with the latest smartphones, but my mobile phone, the first one I had was a very basic Nokia, would last for 1 month on standby without recharge. And that's it. So things have gone backwards. You see people running around airports trying to plug iPhones in. I don't know how long the battery lasts, but batteries are a problem. On a laptop, I've got a laptop here, the battery lasts 7 hours. I can work for 7 hours without recharge. Incredible. That's down to the design of the devices inside. So you can design for low power, for portable operation, but you can also design for speed. Like in a PC, maybe you're not so bothered. You just plug it into the main power supply, you can maybe go a bit higher power. But low power we need, because if you get too high a power, as we'll see later, you get too much heat generated, which will kill devices. Digital, if you make an analog circuit like an amplifier, once you've made it, it's more or less fixed. Maybe change the gain, something like this. You take a digital circuit, you can reprogram it. Your mobile phone doesn't work, you can probably get an update. Or your car engine controller breaks, you can get an update. Reprogram it from externally, or maybe even wirelessly now, which is good, but it could be dangerous. If someone could reprogram your mobile phone and wipe all the numbers off, they could hack into it, like this Internet of Things coming in, security is going to be a major problem. They need to secure the data somehow, which I don't know how to do, and I don't think anyone does. So it's got to be a low cost, and digital's low cost, because once you've made one mobile phone, one Samsung, you can make 1 million, once you know how to do it. So when you get the economies of scale, it's setting up the first one that costs the money. And it's everywhere, everyone's growing up. You're young enough, you have a digital generation. You know, everything's digital, digital TV, digital radio, you know, internet, all this. So you're growing up, and the thing that's, I don't know if it's good or bad, you want instant communication. Having spent some time with your director this week, his phone never stopped ringing. He puts it down, oh, he's a busy man. 20 seconds later, so if you've been disturbed on often, you can't think. I know he's juggling a lot of balls, as we say in the UK, but sometimes instant communication isn't good all the time. You need to take a break from it. Put your phone down, go for a walk and clear your head. Or sit at your computer and do something. So how do we stay ahead of the game? Well, people are struggling, as we'll see in the next few slides. Technology is marching on. People said it would never march on from the 70s to the 80s to the 90s, and it still continues on. People struggle to keep up with how to design such complex systems. So Indian's actually very good. They've got a lot of expertise in design software, a lot of software houses helping. It's the design simulators that need to be more mature than the design itself. You can't really build a new design if you haven't got the design tools. So this afternoon, I mean, some of you may know how to use the tools, but we're using some of the latest tools here. And I'm happy to say this NIT has got really good design tools, but maybe not good for the next generation. I think they go as far as 10 nanometers, which is pretty good. But the tools for 7 nanometers probably don't exist. So the tools need to grow, and the testing ideas, which are behind as well, before you make the chip, really. Otherwise you don't know it's going to work. You're probably young enough to know that Intel made a chip once, and it made some error. It's a CPU chip. If you divided a couple of things on one particular operation, it gave a fault. On one of the pension chips, it lost a lot of business. Just one person did it. 99 times out of 100, you never do that operation. You have to recall all the chips. Because there's probably one mathematical routine slightly wrong. And as things get bigger, this will happen more often. So the tools need to find all the faults in the chip. Not just hardware faults, processing faults. An ECAD, as we'll see, ECAD is normally, because it's been matured to do clock systems, you know, synchronous systems. If you want to do asynchronous systems, ECAD's only been tried for the last 10, 20 years, so it's not good enough. Asynchronous CAD is still developing. But I don't know about in India, if you learn to drive, looking at how people go on the road. In the UK, we have to learn to drive. You're not allowed to go in a car without an experienced driver, and you have to put an L plate on. Yeah? So if you want to design electronics, you can't just go straight onto the CAD tool without the basic knowledge I'm trying to give you as part of this course. So You need to learn about how to do the design first before you go into the CAD tool. Otherwise you're driving, it's worse when you're driving blind. Maybe that's safer in India, I don't know. Well, as a passenger maybe safer. Sorry. Yes, sure. Please, come on. Yeah, no. Yeah. He's poor. He hasn't got access to it. It's very difficult. Yes, you can't. No, really, no. You need the resources. You can think about the problem, but you really need resources to solve it. I mean, without a CAD, you can do simple circuit design, but if you're doing a circuit with 1 million transistors, you can't do it on paper anymore. I've made circuit boards, on paper. You draw the circuit and make the circuit board, then you draw the chip. I made a semi-custom chip, and you print out the chart. But it's too difficult. You have to get educated and move to a company. A one-man band can't really start a company like this unless he's a genius and he's got funding. So the answer is it's difficult. Not impossible, but very difficult. Yeah. 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 You can try, yeah. Good luck. Yeah, it's difficult, yeah. So let's just finish this introduction. Test and validation. Well, in university type environments, it's changed slightly. You used to build a circuit on a breadboard and do the testing. So you learn how to put the wires in. The common student probably don't put the power on. You make a circuit on a circuit board, you haven't put the power on, you've got to remake the circuit board. Because people might get snowed under making the logical design. Quite often people forget to put the power supply on. Anyway, that's a common problem. So in simulation, you can do some functional testing. Functional testing means how does it work? If it's an AND gate, 2 inputs, 1 output, you put the logic in, you look at the output. It's not just logic. Now we're talking about speed. And you've all learnt about it. I'll do a bit more this afternoon in the lab. All circuits have propagation delay. Going from 1 to 0, you've got a rise time, then a fall time. And as things get smaller, these become more important. Because they're probably a bigger ratio of the overall picture. But we're going, instead of going from 0 to 5 volts, we're only going up to say 1 volt. So the edge is shaping, but the speed is going up. The clocking is going up every time. So the edge may be similar, I've not checked it, but so you need to think about these things. So simulation will help, but simulation will never be building the product at the end. The simulation is only good when you build the product and it works. Simulation won't cure everything, but it's a good start. So testing is difficult because size of components are reducing, so basically there's more components. So as I said before, if you've got a multi-chip module, you can't get inside the module. If you've got a ball grid array, you can't get underneath to probe the connections. So you need electronic probing. We're going to do a bit on this afternoon on testing. So instead of testing with a mechanical probe, we're going to use the electronic probe. Okay? So this is the thing which, again, universities don't concentrate too much on. You'll do the functional testing if it's an AND gate in the lab, put the inputs in, look at the output. You might look at the speed, but it's very important where you're going to put this circuit. Environmental issues. If you're going to use a circuit in India, as opposed to the UK, what's the temperature range? Will the same temperature range apply in India, UK and Norway? It won't. So if you're making a car you want to sell anywhere around the world, you have to think what temperature range is going to work under. And not just that, what's the vibration? Now driving on a nice smooth road in England and the roads in India, you've got different vibration. Don't care what you're saying, so you have to design for vibration and also humidity and maybe dust. I know in here it gets dusty and very wet. If you go to Singapore, it's like 100% humidity. to keep the humidity out of the circuits, water and electricity, bang, not going to mix very well. So, environmental issues, I'm just going to touch on them because I've done a lot of environmental testing with my own students recently, and it takes a lot of time. How long do you think a car lasts? How long would people keep a car in India? Have a guess. 20 years? This ambassador car, see, how old is that? That's maybe 50 years? It's still going. It's like the phone. It's very strongly built. Maybe not so economic, but it survives. It's designed for the conditions better than maybe some modern cars. So, how do you validate it though? So we've got to think about it. And later, well, not so much on this course, but you could do a separate course on green electronics is coming in. By green, I mean, how do you design so you can recycle the electronics? So at some point, after 2 years or 3 years, you'll throw your mobile phone away. It might get used in a poorer country, but after some time in the future, it wants to be recycled. And some very rare minerals in the electronics want to get out. So, yeah, it is, yeah. So I've seen ideas now to put circuits on wood. So instead of the normal circuit on wood, because you can recycle it easily. And different materials are coming in, but it still can't be what we've got already, which is a flame retardant material. So it's not so easy to recycle it. So it's coming in, recycling. And by green electronics, that's all to do low power as well. The soldering material used has to be green, so it's probably lead-free. It might not be solder, we might glue it on with some glue, there's some conducting glues coming out now, but we're not good enough at the moment. So what I'm saying is, if you're doing a validation, you've got to look at the environment, and you want a good chance through its lifetime. So if a car, you say you keep it 20 years, you want it to work 20 years. If it's a phone, you keep it, say, 5 years maximum, you want it to make sure it works 5 years. So I'm asking you, how do you test it for 5 years? You want to wait 5 years for the next phone? You're not going to wait out. You want the next phone from Apple or Samsung or whoever the minute you can afford it, when your contract runs up. So what we have to do, and we'll do a bit more throughout this course, you have to accelerate the testing. You can't wait 5 or 10 years or 20 years to see if the circuit still works. And for aeroplanes, they might want to fly for 30 years. You can't wait 30 years. So there's ways we can speed this up. So I've already jumped the gun. Here it is. Accelerated testing. So I want to reliable for a certain time, a long period of time. So again, we can't wait this long. So how do we accelerate live testing? We overstress the device. So say your mobile phones are in your pocket. Temperature in Alabama goes from, say, 2 degrees C in winter minimum to say, if you leave your phone in the car with normal conditions, maybe up to 40, yeah, 40, 50 maybe. Well, normal commercial range used to be 0 to 70. The testing we normally do is minus 40 to plus 85. So it's stressing it a bit more. Some other circuits we've done a minus 40 to plus 130 degrees centigrade. So because you're stressing it more, or you're vibrating it more, if it's a vibration test, it should fail. But it's still, I don't know if I put the time on. It is, well, it's sufficient, but it still takes a few months to do the test. But we can't be 100%. If you're a manufacturer, car manufacturer, you're confident, you've got the expertise. A lot of empirical formula in this. So again, it's not textbook engineering, you learn from your experience. If you do a certain vibration test on an engine management system for a car for say 2 months, and it passes, you know 99.99% it's going to last 10 years. You extrapolate it. Extrapolating is very noisy. So you're going on experience as well as the formula. And the formula is a bit prone to error. A lot of experience in this. Same for semiconductors. I'll show you some slides this afternoon from Motorola on how we used to test the chip. So if the device on the test fails, this is a problem. We need to know why it failed. If your CPU in your mobile phone fails, and the reason is we have failure analysis, which is something I'm going to touch on in a couple of days' time. So failure analysis will take a product that And it could have failed when it's doing one of the tests, so it could have failed in the market, in the field, which is what you don't want. Because then you get a bad reputation. If all of them Suzuki cars are parked on the side of the road, next year no one's going to buy any. Same if it's Jaguar Land. Doesn't want a Jaguar Land Rover in the UK. If they're all on the stock, no one's going to buy it. They'll buy something else. So how do we fail analysis? Well, fail analysis at the solder level is actually normally you find out where the problem is and cut the board. Because the fail is hidden. You can't see it from the outside. Cut the board open, polish it, and do some type of microscopy to see where the joints failed. But if you cut it in the wrong place, you can't see anything. So again, a lot of expertise there. Fail analysis you could do for 50 years and still not be an expert. Really tough. It involves metallurgy, material science, as well as engineering. And again, all this stuff, you're not just an electronic engineer nowadays. You have to do a bit of mechanical engineering, bits of environmental engineering, and so on. Don't just think you can just do electronics. We all do programming, also a bit of computer science nowadays. So, a little bit of the last day. Last day is a bit easier, on what equipment we might use to do the testing. But equipment's very expensive. Industrial equipment, talking about hundreds to millions of pounds to buy it. So a lot of people might rent it. But big business in that. So now I'm just going to look ahead as I see things are developing. So there's no doubt the devices are shrinking in size. Okay, we looked at the mobile phones, how it's gone down over that time. From 1983 to 2017, the transistor size went down by a factor of 100. Remember those slides? From 1 micron to 10 nano, the size of the individual transistor. But that's just the sort of gate size or the line size. That's only in one dimension. But transistors are 2D. So it's a square level. So that factor of 100, 10 squared becomes 10 to the 4th. But now we're going into the Z plane. So that's also going by about the same, more or less. So now we're talking about 10 to the 6th. So transistor density by a million in X, Y, and Z. So this is incredible engineering for semiconductors. This is clearly people, incredible. So all these designs, you may have heard of it, you may not. It's a famous law called Moore's Law. Okay, you got a question? Can you give a microphone? Is it working? Just shout it. What can be these? Sorry, I missed it. Tell you what to use. Yeah, I'm going to talk about it on Thursday or Friday, but briefly, the testing devices for heat is like a big pizza oven, like a big oven. It's a heating and cooling chamber, and for vibration it's like a big piston that vibrates. So shaking machine we call it. So big mechanical devices for shaking, like a big motor you could say, and a big oven, but it's a cooling and a heating oven, the refrigerator and oven combined for humidity you have a spray system. Actually spray water, and maybe salt water, you get salt on the roads in colder countries for ice. They actually have salt spray. Anyway, I'm going into that a bit more on Friday, but I can discuss it later. So the Moore's Law, if you haven't heard of it, he's saying he made a prediction. It's only a prediction, and this guy was one of the pioneers of semiconductors. You'll read about him on the internet. He worked for Fairchild, then he worked for Intel. He started Intel, he spun it out from Fairchild, and he said, well, he noticed, and this is talking very early days in the 70s, number of transistors on a chip will double every 2 years, and we're just at that point gone to small scale integrated circuits, and no one believed him. So some guy coined it, and we're going to call it Moore's Law, because it started to come true. And then if you look at it, it's even better. If you look at the last line, the chip performance is based not just on a number of transistors, but switching speed, and together they double every 18 months. That means every 18 months you get more transistors and more speed. This is like having ice cream every day. Incredible. And no one said it would last. But Moore's law is a straight line, and people thought it would tail off because the technology couldn't do it. The technology steps have stayed ahead, so Moore's law keeps going to a straight line. And even though it's an empirical law, he just said it, something he noticed at some conference. It's set in folklore, so you don't conceive that very well. So if you look at the first sort of autumn when he started in the 70s, the first sort of transistor, I'll show you a bit more detail, about just over 2,000 transistors on a single chip. Okay? All these slides will be available if you want them later, so you don't need to take too many notes. So if you look at towards the end, in 2013 you got 2.5 billion. If you go on the American billion, 2 to the 9. That's incredible. Can you imagine designing a chip with 2.5 billion transistors on? So that's quite an old slide. 2011. Remember, it doubles about every 2 years, say. So 2013, that's now about 5 billion. 2015, which is now, is 10 billion. That would blow your mind, trying to design that. So you probably can't design it on your own. We're going to break the design up into partitions and probably have teams working on the subsections. This is how I would do it, but I'm not sure if that's exactly the correct way. And the latest chips have come out with this number of transistors on, about 10 plus billion transistors. So it's interesting how we can achieve such things. So another thing comes in as well as the Moore's law. It's like another empirical law called this Dennard scaling. He's another semiconductor pioneer. And he was in the background, but all of a sudden people said it's not just Moore's law, it's about more than that. More than Moore, used to call. Because they said Moore's law would finish. If you go back, everyone was saying for years, even there, say, oh, that's going to finish and curl off, and it's going to finish and curl, it's going to finish and curl off. It never tailed off. Because the technology people always came up with a solution. It will tail off eventually. But maybe not in my lifetime, but it will, because we're running out of things we can improve. But people have said that for the last 40 years, so we'll see. In your lifetime, you can see what happens if it does tail off. So this Dennard scaling, we'll just run through it very quickly, because you can read it on the slide there. So it links the power on the chip requirements to the area. Since voltage and current are both proportional to length, if you think about how you make it on a chip. So power performance per watt, this is what he's saying, will grow in line with transistor density. So we need to look into it a little bit further because it still doesn't mean too much. So he predicted that transistor dimensions, and every generation is about every 2 years nowadays, to go down by 0.7. That means 0.7 in X. So because it's X and Y, 0.7 squared is about 0.49, so about 50% reduction. So change it in X, you change the area. The square law is very good for engineers. We get in double the, well, more than double. So the area goes down, so the delay goes down by 30%. That means the switch faster, which is what everybody wants, fast switching. Operating frequency increases by about 40%. Now, some of you may have done CMOS. What happens to CMOS if you turn up the operating frequency? Does the current go up or down? You know? You've got a CMOS inverter, you clock it. If you turn the frequency up from, say, 10 megahertz to 20 megahertz, what will the current do? Go up or down? What do you think if you speed it up? It's going to go up, I'll tell you. It just about goes up as a straight line. So as you double the power will go. So by making the transistor smaller, taking less current, so that's the double gain. But when the frequency goes up, that's the opposite way. That's got to generate more power. But overall, they tend to cancel out. So if we just look at the end first and then come back to that, it means for every generation, transistor density doubles, which is what we just said there, up to 10 billion by about now. Circuits become 40% faster, roughly every generation. I don't know what we're up to now, tens of gigahertz. Coming into microwave technology. Power consumption stays about the same. How amazing is that? So power consumption didn't stay the same. It's about 100 watts now on the big chips. If you've got 100 watts in a small chip, about 2 or 3 centimeters by 2 or 3 centimeters, you can't get rid of the power. 100 watts is a lot in a chip. But electric field stays constant by reducing the supply voltage. If you don't reduce the supply voltage, different problems are coming in. Supply voltage stays at 5 volts. It's to do with electric breakdown. You've got 5 volts, got a very small 10 nanometer junction. Work out the volts per meter, and you'll find it fully breaks down the silicon or the semiconductor material. So voltage goes down, 3 volts, 2.5 volts, 1 volt. You can only go down so far. You need to get over the silicon barrier to switch. So now I was actually talking to your colleague the other night, and now we've got junctionless transistors. To get over that barrier, silicon, you need 0.6 of a volt to switch a transistor on. So it means you can't have a logic level less than 0.6. You need some margin, so maybe 0.8 is the minimum, I don't know. I'd say I'm happy with 1.2. But you need a difference between logic north and logic 1. So power reduced by 50% at 1.5 times the frequency, and the energy produced. So this Dennard, and again all these rules, he quoted these rules a long time back, that remained true, like empirical formulas. So these guys could predict ahead. It's incredible how they did it. So progress, we're nearly finished on this section. So, and then I'm going to do a design example on the board. So progress is on microprocessor. I just picked out 2. This is before I was involved. The first microprocessor I worked was the Intel 885, which was one of the first 8 bits, which is very good for teaching, very good for learning. It's not. But before that, Intel produced this 4004 in 1971. I think it's a 4-bit microprocessor, mainly designed for a calculator. It's not in general use really, but it's a start. Because before you had microprocessors used to buy discrete logic, you had the trouble putting it all together on a board, making the board, soldering it, although it might not be reliable, you have to test it. You buy the microprocessor, you buy the clock, some memory, you're working. Very quickly you're working. Then after microprocessors, microcontroller came in, everything's on the chip. You just program a chip and just very good, very cheap. Anyway, it's a 10 micron line width in those days, and it's got just over 2,000 transistors, 2,300. That's the state of the art. Now, in the chip area, 12 square millimeters. So say 4 millimeters by 3, within just about picture that. Quite small. This is the new Intel. I looked this up before it came away. Due out about now. This stands for Q4 2017. It won't tell us how many transistors are on the chip, because it's a bit secretive and it's new. We'll find out maybe in a year. But it's 14 nanometer line width, which is more or less state of the art, 14 or 10. And it's estimated there's, from me, 10 billion transistors on the processor. 10 billion. But I don't think it's all on one chip. I think this chip's going to have maybe 4 or 6 sub-chips on. So we'll spread it out, but even so, if you had 10 sub-chips, there's still a billion transistors on each sub-chip under the package. So pretty impressive. So this is the final slide, I think. So 2018 is when the 10 nanometer technology will be in the market. The new buzzword now, 100 million transistors per square millimeter. That's on the device. So I can just about think of a millimeter square. It's the smallest graduation on a normal ruler. Square it, and you get 100 million transistors on that 1 millimeter. And just to show you how it's advanced, from 2008, which is only 10 years ago, was 3.3 millimeters a square, using 45 nanometer technology. So in less than 10 years, it's gone from 3.3 million to 100 million. So the next generation, I don't know what it's going to be. So one of my final messages from this part is synchronous design can't go on forever with these scalings. You can't get the clock around that many transistors on the chip. So I think the only way we go, and I've done some work on this in the past, multi-chip modules are in multiple chips on the CPU. 4, 6, 8 will be common in the next generations. But parallel processing is going to come in more and more. Parallel processing means you have maybe 2 identical processors working on a problem that you've broken down into parallel. So it's a different way of programming, maybe 4 chips, maybe 8 chips. But it means the chips can be smaller. So when you do parallel programming, the chips can be very fast. The bottleneck then is each chip has to talk to each other. So the more chips you put on, well, you know, Indians talking to each other can become into chaos. You've got 8 chips talking to each other, harder than 2 chips. Got off to the competition. So parallel won't cure everything, but parallel will cure a lot of things. And I think other technology will come on. Semiconductor technology is still moving on. Don't get me wrong, it's not dead, but people have been saying for years, bioprocessing, using biomaterials, cells will come in, but we don't know how to harness that yet. So there's work going on. And you've heard of probably quantum switching, like one electron might switch, but you can make it switch, but how do you put it? But you need equipment the size of this room to make it switch. One electron, it's not portable. So it could come on, but you need not yet. So I think, and I've thought about this, optical switching must come in. Because I've done a lot of work in optics in the past. If you've got an optical beam, parallel beam, it's all in parallel. So you put that through a spatial light modulator, all the processes in parallel, it's very fast, speed of light. The bottleneck is how do you get the data into and out of the network. And again, people are working on that. Optical may come in, or some new effects could come in. You've got to have an open mind. I mean, I don't know what level you are, but if you're doing a final year project or some research, keep an open mind. Don't say, because Fred did it this way, that's the right way. It might be the right way, but just have a quick look. Give it all the other ways, and then you might take it on even more. Oh, it's not quite the last slide, sorry. So limits, I just want to, I like synchronous design, don't get me wrong, but I really do like asynchronous design, which we'll do tomorrow. So it's quite nice how we do it. Clock speed, I did mention. You can't just keep turning the clock up and up and up. As you increase the clock, you increase the power consumption, and the devices can only switch so far. Every device will have a limit. Even if you switch at 100 gigahertz, you can't go 2 gigahertz, 200 gigahertz. You'll have a limit. With switching, clock skew means if you've got clocks going across a big circuit, the clock on one side of the circuit will be different to on the other side of the circuit. And that will give you major problems. So a lot of the manufacturers now will have clocking systems where they're trying to keep the clock line up. Everything's going at the same clock or multiples of that clock. So if that gets skewed out, you can get the wrong answer. And as speed goes, skew will be more difficult to handle. Speed of light, there you go, how fast is that? How fast is that? How long does it take for the light to go that far? Any idea? That's supposed to be 30 centimeters. Do you know how far that is? 30 centimeters. Yeah, this is 30 centimeters. Right. How long does it take for light to travel 30 centimeters? Nearly. How many? How many? One. I'm not, yeah, that's good enough. Well done. So, to go 30 seconds with light, there's nothing to go faster than that. 1 nanosecond. Got some more questions? Okay, that's it. The come and go. Brains, possibly, yeah. But do you want to donate your brain now? It's the ethical problems. But you're right, if we can grow brain cells, or neural networks or brain, yeah, that's it. So where's your research topic? You research it and come back when you're a millionaire. Yeah, it's a good topic, yeah. That's right. Keep an open mind, literally. And so am I going scientific. That's good. Yeah, brain computing. Keep an open mind, no one really knows. Again, it's biological. No, because the trouble is, I don't want to go into that now, but no one really knows how the brain works. It's such a complex thing. Just we're glad it keeps working. As long as we can. So anyway, let me just get back to the speed of light. I just want to concentrate on this. So the famous American lady used to go around with pieces of string cut to 30 centimeters or 1 foot. Very famous. I can't remember her name. You should give it out to the students. You say, this is a nanosecond. And this is why we used to make the Crays built, the Cray computer. They're built around the sort of central axis. So all the interconnections are in the middle. It keeps the connection short. Okay, it takes a finite time to move down on the connection. So this is going to be a major problem. I've told this to my own students. Speed of light or signal transmission is going to take a certain time. So if you think of, again, 30 centimeters, about 1 nanosecond, plus or minus, in a copper wire or semiconductor, you go down to 3 centimeters, which is the size of some modern chips. It can be 3 centimeters square easily, maybe bigger. And it may go to chip scale wafers, 300 millimeters, 30 centimeters diameter. How long is it going to take then to go on the circuit a tenth of that? Well, it's going to be a tenth of a nanosecond. So 100 picoseconds. So the transistors switch in at 100 gigahertz, I think that's about 10 picoseconds. You're going through 10 transistors, the signal will arrive before it's gone through the transistors, or vice versa, depending on the connection. So connection routing will become very, very important. You don't keep it short. And again, that's the same for any circuit, synchronous or asynchronous. You need to keep the connection short. So if you do an auto routing, some auto router will say, here's your chip, I've routed all your chip, there's one gate I can't route. I'll put it in the top corner. You might just do that. You use that last bit of silicon, then it routes the connection up there to the chip and back. By the time it's come back into the gate, another signal's come along before it, it goes out of sequence. And this is the sort of transmission time we need to think about. So be aware of auto routing. Don't think auto routing will cure everything. So that's speed of light. So signal transmission and switching times need to be taken hand in hand. Transistors will speed up. You can't speed up the speed of light. So that could be a crossover in your lifetime in the next 5 years. Power in excess of 100 watts, which we've got to already. How would you get it out? Well, look at your PC. You've probably got some quite complicated fan design that's been developed for 20 years to get the heat out. A very turbo type fan, but it's only air cooling. So that type of fan, say in a hot country like India, will need to be bigger than in a cold country like Norway. And now we're talking about water cooling. That's been talked about the last 10 years. You may have to spray water on the back of the chip to get the heat out. But again, that's only good if you're in a cooler country. So heat in excess of 100 watts is going to be difficult to get out. And already I think, and if the fan has stopped, everything gets stopped. So the chip core temperature has to be kept down. Again, I've got a bit more on this later on, but basically if the chip core temperature goes up 10 degrees, the chip lifetime will go down by about half. You've got to keep it cool. Yeah, and it could be worse than that. So, and again, I said it at the start, what's the limits to the design? Well, the design tools will have limits. Design tools, even if you're a clever designer, can't do everything. And you really will have to break the problem down into smaller parts. You can't design 10 billion transistors in one design. I don't think a simulator could simulate it. Just need to break it down so the simulation doesn't take too long and you can do the design. So it's partition design, I'd say, is how we would do it. And fabrication, how would you make these chips? 10 nanometer chips, and you're going to put, you tend to, now we've gone to 30 centimeter wafers in some of the fabs, so the wafers are disk. So you're going to make a number of silicon die or semiconductor die on the chip, and you're going to put all these different designs down, probably the same design of chip. It's very difficult to make that. The line, the equipment to make is very expensive, so semiconductor fabrication is very rare, so very expensive. Not many places can do it. I think in Europe there's only 2 or 3 places can do it. In America maybe only 1 or 2. In the Far East a few. So the big business, you can set one up, but most people now don't want to do the fabrication. It takes a lot of money to set these tools up, and in 2 years they're out of date. You have to set up the next system. So it's an opportunity for any country to set it up, but you need money, from the government or whatever to set up the initial process and expertise of it. And as things get smaller, you go from, on the circuit board level, solder joints, multi-chip modules, how would you test the circuit board and how would you test the chip? Well, they'll have some road mapping exercises, and road mapping will say that the testing technology is always behind the technology available. So they make the chips, and they make the circuit board, but we haven't got the tools the microscopes or the testing machines to test them. So you've got to really keep up with that as well. So test and validation technique. Okay. Any questions? I'm going to do a quick exercise before lunch, the design exercise next. Unless you've got any questions. Yeah? Yeah? Photonic, yeah. Well, one hazard is this. Light can blind you. That's the first hazard. Anything to do with lasers, health and safety. Don't point a laser at people of aeroplanes if you're doing... But that's what, photonics, yeah. It's usually the interface. The photonic switches themselves are working at the speed of light. So the problem as I see it is how do you get the data into and out of? Because you've got a photonic device, you may have to make light in the first place, process using light, then convert light back to electricity. Possibly, I think it's a bottleneck, yeah. But then you can go parallel. So if you can, I mean, it's possible you could have a system where you've got an optical computer core and some type of fiber optic into an output where you fire and multiplex it, but then it's not parallel anymore. It's not been solved, I don't think. I was keen on this, but the device is a bottleneck, not the light. But I think it will come in for certain applications. So photonics is a big field. You could make a career in that field. Well done. Okay, so what I want to do next is just, I think I've put it on the next slide. For those people that know this, I'm sorry, but I'm just going to show people that don't know a standard state machine design process. A lot of you may know this already, but I'm just going to run through it so everyone knows when it gets to the laboratories a little bit more. So FSM means finite state machine. Okay, so just to put this in a nutshell, every digital circuit can only have a number of states. 10 states, 20 states, 1,000 states. So it's limited. And as a designer, you try and fix it. So what you do as a designer, you have to specify the states to start with. Or if you're in a company, your boss might come down and say, I want you to design something to do this. And you may have a logic diagram or a truth table, or you may have things. So then you design from scratch. So you design the states, and the design procedure, we give a state number. Each state should be unique when we start out. We draw this state transition diagram, STD. This shows how we move between the states, a bit like moving between the station with a train, A to B, then B to A to C, and whatever. It shows you what's required in terms of a ticket price. And not to move it to this state, and one will move it to this state. So it's quite visual. So this state transition diagram is used in other things like communication. We used to use it in the old days. Using the telephone to pick up a handset when you had handsets, and what's the procedure to make the phone call. So it's used in other systems as well. But for electronic, is to work out the sequencing. So when you apply the clock, if the inputs are in a certain way, it'll go from state A to state B. If in a different way, go from state A to state C, and so on. And if nothing happens, it should stay in the same state. It's got to be stable. Okay, so the key to this is, because it's a finite state, it's clocked, it only changes when you have a clock, which is an advantage and a disadvantage. So we draw the state table, then the state table is in sort of English. It's showing you the state between them. You can't design in labels, so then you have to go to the assignment table. It's become this, and then we've got a final design. So I just want to run through them very quickly, and then after that I'm going to show you the two basic block diagrams for state machine based on two different systems. So I'm going to write on this board. So we can leave that there. we're going to design an odd parity checker. You know what it is? Yes? Some people know, some people don't. Do you know what parity is? Some people do, so let me just, some people obviously probably know. Normal definition of parity is the number of logic ones in a sequence. Okay? So that is even, yeah? So you got 2, so you got 0, 0, 1, 0, so you got 1, 2. So you've got an even number of ones, that's even parity. Okay? If we do another sequence, 0, 0, 1, 1, 1, that's got an odd number of ones, so that's odd parity. So we used to use it a lot. Not probably still do, but you're too young. But in the old days, when we typed computers, we used to use teletypewriters, like a typewriter that communicated on a serial bus, and we had a parity check bit. Because the communication was quite noisy in those days. Now it's all digital, it's fine, you don't get any problems. So the parity checking had not to be added in. So say you've got 7 or 8-bit data, it just adds up the number of ones in it, and it gets an odd or an even parity, so it checks it. So it's really used for transmission of data, but it can be used for anything, in arithmetic or whatever you want really. So I'm just going to show you how you can design a simple circuit to check. The stream coming is a continuous stream, not just a fixed stream. So it's fairly simple. So design. Okay, so what we get when we're designers is you look at the question. Okay, we've got an input stream. So how many inputs have we got? 1. Okay, input stream is serial input, so only 1 input. That immediately simplifies the circuit. So we've got a circuit, so we've got an output, and the stream. So the stream is like a drum, it's just going to come in, 0, 1, 0, 1, 1, 0, and so on. So if we're thinking about a number of states, because we could only have even number or odd number of bits, we can only have 2 states. So we keep it simple. So we do the state transition diagram first. So start off, normally we'll draw the state. So got an even state inside this bubble, and we put the output down. We'll say the output's 0 for even parity and 1 for odd parity. Okay, so then how do you move between the states? So these are bubbles, so you draw like the state arcs. So if you're in the even state, you move to the odd state, you're looking for a 1, logic 1 to come in. So that's taking it from an even number to an odd number. If you're in the odd state, you're looking for a 1 to come in from that state to go back to there. So if the input was 1, 1, 1, 1, 1, you just cycle around, around. Then when you get to the north, yeah, well, say you got two, say you're up to there, and this one even, then another one comes in, you go back to there, the next one comes in, you go back to there. So it's cycling around. So, yeah. This is the state. So normally people don't show it, but on this I'm going to show what happens if we stay up north, stay at that state, and this one stay north, stay at that state. So just to describe that circuit, it can only be in two states. So just one more line to squeeze in. So circuit can be one of two states, even or odd. When inputs are 1, we switch between the states. As I said earlier, even add another one going to an odd parity, add another one go back to even parity. So if input is a naught, we stay in the current state, but we've still got the same number of logic 1s. And then the output associated with odd and even, I'm showing them a state bubble in here. And again, this is the first thing, as well as doing the bubbles, we decide as designers what the output should be. We could have chosen 1 or 0 the other way. As long as you've got your own specification and you understand it, that's fine. But once you've done it, you don't want to change it. Okay, so that's for specification. So input values that cause a transition are represented by the arcs that I've shown on the diagram with their associated inputs. So one thing is missing from that design now. Anybody any idea what's missing? Start. Well done. Most people, and a company called, I can't say the name because it's an unknown semiconductor company once made a big chip, very big chip, and forgot to put a reset signal on it, reset input. You can't reset to a known condition. You don't know where you're starting from. So, if you look at this, and again, we're not looking at textbook engineering, which is a bit more like a textbook type design. What's the real design practice for? You have to reset a circuit to a known condition. So you may see that design or similar designs in a textbook, but we never put reset on. So you put a reset, and I'll decide to reset to north. So when we do the final circuit, we're not just going to do the sequence, we're going to have a pulse, start it at 0. Okay, and that's the same for simple circuit like this or the latest CPU. When you boot up your computer, you want to reset it so it hopefully starts from the same point. Well, things can go wrong. Never mind. So we'll just continue on with this. It won't take too long and should take us up to the lunch. Okay, because I know you all, did you enjoy the high tea? So you're probably not so ready for lunch, but I'm sure we can enjoy it in 10 minutes or so. So I'll just rub out the top and we'll do the design. So we'll do the state table. So again, the first time we do it, it's not so easy. We've only got a present state and a next state. We've got one input, which is on there, and one output. So let's look at the states. So we have even states. If we've got even states, the input coming in is only a 0 or a 1. Okay, so we know we need two even states. So even state with a 0 and even state of a 1. Okay, then the odd state, again we've only got two inputs, a 0 or a 1. So we've got odd state, a 0 or a 1. Now you're going to help me fill the table in, just so we don't go asleep before lunch. So if we're in even state, the input's 0, what's the next state? You're very hungry. And what's the output? Output is 0, doesn't change. Okay? So now you're in even, you've got a 1, so this time it's going down. So that's odd. And the output this time will change. So the beauty about clock design is the output won't change until we have this clock in this type of design. Now the next one, odd, and a 0 comes in. So we're going to stay in odd, yeah. And so the output stays 0. and odd, and the 1 comes in. You're going for lunch, so you're going for even. Have I made a mistake? You see, I'm just testing. Okay, so present state odd, input is naught, we're in naught. I'm getting confused because we're already in naught. Anyway, so we stay there. This guy's good. You can do the last one there. So odd with a 1. This time we're going back up to even. And this should be a naught. Okay, so that's, oh sorry, that should be a 1. Yeah. So 2 things, I made a mistake there myself. 2 things we need to think about. This is the output, so the mistake I made is here. Okay. So it just shows you simple design can make simple mistakes. So what we're doing, present state, this is the present state output. Okay? So if we're in even state, the output is always naught. If in the odd state, the output is always 1. So we do the clock. When we do the clock, instead of the next state, with a naught, we're still in even. If we're in even, the next state we're changing, going to odd. But we don't change the output till the next state. That's the beauty of the clock. It's clocked through. The feedback comes through the clock. So now we've got that, we can't design, we need to decide what values do we put in here, binary values for even and odd. So we've only got 2. So we only need 1 bit, and also 1 will cover it. If you add 4, you're going to need 2 bits, and so on. So I made the decision, whether it's right or wrong. It doesn't matter, it gets the engineer's decision. Even as an output of naught, so I'm going to make even naught. Odd as an output of 1, I'm going to make odd 1 in my design. Could have chosen the other way. The difference probably be you might need 1 extra inverter in the design. So you could try both ways if you've got time. You know, if we're working on the design industry, try both ways, it won't take long. just so you know where that comes from, we're assigned even on the present state to a naught and not in the present state to a 1. So now we've got the table, so we can now do the design. So can you see the gating? The experts on logic? What's your favourite logic gate? You've got two input logic gates. You've got OR gates, AND gates, NAND, and XOR. Can you see XOR there? This is the best gate going. So we can do by because we know lunch is coming. So I'll do it over here. So, straight from there, I'll go through it and I can say what the logical expressions are. The next stage. So if you look at this as a sort of truth table now, if you look at those two, if that's the outputs and the inputs, put another line there, we can see this is the truth table for exclusive OR. When the inputs are different, we've got a 1, when the inputs are the same, we've got a 0. So this is the equation. Next state, which is what we're trying to get there, is present state exclusive OR with the input, and the other one, you see this one just follows the present state. No gating required. Isn't that great? So output here is just the present state. Final design. There's one thing missing. Can you spot it? Reset. That's right. I left it off deliberately just to see how desperate you are to get your lunch. So, as I said, textbook design is like that. Simple. Input, exclusive OR gate, clock, odd parity output there, but we haven't set it up to a state. So we need to initialize So initialize. Normally in old-fashioned logic, the reset was always low. So I've called it not reset. That means going to pulse it low to start the design. So we show that was a bubble, which is like an inverter on our input. Okay, so now you all know how to design. You'll be experts this afternoon after a nice lunch. Any questions? Okay, I think it's time to take a break, so that's fine. Thank you for your attention. We'll continue this afternoon, I think at 2:30 or thereabouts, Indian time, you know. Plus or minus half an hour. You know. I'll be here, don't worry. And I hope you enjoyed it. And I hope you enjoy your lunch. Okay, thank you. Okay.